Welcome everybody to today's IES webinar. With emerging science, technology and regulation, jobs in the environment sector are never static. This webinar series, A Day in the Life, is going to be sharing stories from environmental professionals about how work has evolved and how it may change in the future. Today, we're joined by Mónica Rivas Casado, Reader in Environmental Systems Engineering at Cranfield University, who's recognized as a leading expert in the use of UAVs, i.e. drones, as a data acquisition platform to improve flood risk management in the UK and internationally. In today's webinar, Mónica, who is, as I say, Reader in Environmental Systems Engineering at Cranfield, is going to be sharing her perspective on the nature of her work as an academic working with water systems, what it was like in the past and how that kind of job may look in the future. The webinar is part of the fifth theme of our year-long Future of ES23 Horizon Scanning and Foresight project, The Job, where we're looking at several key environmental specialisms and we're asking what the job was like in the past, what it's like now, how it may look in the future. Throughout the year, we've been bringing together interdisciplinary perspectives on horizon scanning from across the environment. And the work is supporting the sector to manage risks, to plan ahead, and to work towards a better future for the environment, achieved through transformative change. In just over a month, we'll be publishing a vision statement on the future of the environmental sciences to bring all of that work together. So keep an eye out for more information on that really soon. Focusing on the matter at hand, though, as always, there'll be a chance for questions at the end of the presentation. So please do submit those in the Q&A option, which you should already see at the bottom of your screen at any point during the presentation. And then I'll ask those questions on your behalf a little bit later on. Thank you for logging in, though. And for now, I'm going to hand over to Mónica.
Thanks, Joseph. Thanks for the warm welcome, and thanks for having me today. I'm here to talk about the significant advances that emerging technologies have brought to the water sector. There are so many things technology can do now, so we don't have to. Unfortunately, given webinar presentations is not one of them, there are fewer things more unnerving than talking about oneself, let alone spending 30 minutes on the topic and answering questions about it right after. So I admit I hesitated when I was first approached to deliver this webinar, but I hope that by talking about my own work, I will touch on insights that are of value to the wider audience. I would like to discuss three main benefits arising from disruptive technologies for environmental engineering tasks. First, they enhance environmental monitoring capability. Secondly, they provide vast amounts of data for more informed management decisions. And thirdly and finally, they are cost-effective solutions to some of the problems we face. So let's look at these 3 points through the lessons I have learned in my day-to-day practice. Before I dive into the technical aspects, let me provide some additional information about myself. In my role as a Reader Environmental Systems Engineering, I work closely in the design and deployment of autonomous systems and robots, which is not quite as exciting as it may sound, but it's still pretty exciting if you share my passion for meeting environmental challenges. My code of conduct aligns with the technology for good principles by using emerging technologies to address environmental challenges. 3 of my priorities are surface water flooding, greenhouse gas emissions, and the degradation of freshwater ecosystems. And that's where my work has focused in the past decade. In a nutshell, my daily task is to design monitoring programs that better capture information about those challenges. Once I have collected the data, I analyze it and I use the results to better inform environmental management decisions. In the past 2 decades, environmental engineers have increasingly been using new and emerging technologies to help with environmental monitoring. Most notably among aerial vehicles, better known as drones, as Joseph said. Drones are easily deployed as and when they are needed and have enabled a much more rapid collection of crucial environmental data. I can personally testify that using on-demand drones has significantly reduced the time I need to dedicate to collecting data in the field, as well as simplifying the whole process. Perhaps the best way to explain the benefits of this technology is to compare the way we work now with the way we worked before it came along. So if you could travel back in time about 20 years, you will find me designing surveys for rivers which had to comply with the European Water Framework Directive. Part of the daily work required the measurement of cross-sections of the rivers, which when the discharge was low, I did using such a high-tech equipment as a rope, a pole, and a metric tape. Even when our budget allowed, I also used a total station to take more accurate measurements, but that was considered a luxury. The images you can see on the right-hand side of this slide show the equipment I used at the time and the type of outcomes derived from the data. In those days, surveying a 1 kilometer stretch of river could take more than 3 days, not to mention a lot of sweat and tears, though at least not usually blood. Nowadays, using a drone means I'm able to survey the same extent in just a single morning. That's assuming the drone doesn't crash unexpectedly, of course. Well, no technology is perfect. All being well, I'm able to reconstruct the river bathymetry with the photography or LiDAR data I extract from the drone, and just look at the difference in surveying equipment and data outcomes on this slide. In some cases, I also collect ancillary data with either ground sensors or aircraft. Most of my time is still taken up by planning 3 surveys, but the data collection is usually completed within a day. So for me, the big challenges nowadays are no longer the demands of data collection, but data storage, and especially the limitations when it comes to processing the data. For example, I usually require extremely high performance computers to be able to process the data and obtain meaningful results. But again, I'm grateful that this technology actually exists. Going back 20 years again, the state of computing was really different, extremely different, to be honest. Like me, some of you might be old enough to remember when floppy disks were the state of the art, or if you were really lucky, perhaps zip drives. If I remember correctly, the capacity of a floppy disk was merely 1.4 megabytes. Today, our surveys involve teras of information, that's millions of megabytes. Thankfully, all that data is a blessing. In many cases, the production of vast amounts of data allow us to spot some very interesting patterns. Back in December 2015, and looking at those patterns, I was leading a project using drones to map the extent of flooding. I conduct an impact assessment in the market town of Cockermouth in Cumbria. Heavy rainfall over an extended period had seen more than 300 millimeters of rain falling over 24 hours, with the result that flood risk management structures were both overtopped and outflanked, and a total of 466 properties were flooded. After the flood, and once the streets were open to the public, we used drones to survey the area. I believe it was the first time drones had been used to accurately map flood extent and damage over such a large area. It was a hectic day, as we had to liaise with the drone pilots in charge of data collection to make sure we gathered all the information we needed for the study. And we also had to liaise with the emergency responders and the army on site to authorize the safe deployment of the drones. On the ground, in addition to the pilots, I had a team collecting photos and GPS data. But perhaps the most important piece of equipment I carried with me at all times that day was a flask of hot tea. You see, to add insult to injury, it was snowing. So even wrapped up against the elements, I was feeling cold under my skin. Basically, we were really freezing, but it was all worth it. The data set we gathered was large and required intensive processing, but the results were very informative and highlighted the importance of considering all sources of flooding, even when an event is largely thought to be fluvial in nature, that is, flooding from an overflowing river. There were significant levels of fluvial and lateral flow flooding, that is, flooding from the rain and the spread of water across the land, with a total of 168 properties outside the fluvial flood extent being affected. On this slide, you can see the affected properties outside that fluvial flood extent, which is the polygon delineated in red. These properties were not initially identified as being flooded, as the emergency responses understandably focus on the fluvial flood extent. But as we demonstrated at Cockermouth, it is important in the evaluation of an event to consider flooding from other sources as well. The problem is not just the overtopping of flood risk management structures per se. Since the 2015 event, I have surveyed the area multiple times to gather additional information with a varied range of sensors, some of them on the ground and some mounted on an aircraft. The datasets are so extensive that we can now use artificial intelligence to automatically detect flood impact and damage. We have even developed algorithms to automatically recognize where rubble from flooded houses was deposited. For obvious reasons, this has got the attention of insurance companies, as they are very interested in identifying properties impacted by flooding and quantifying the extent of that impact. The image you can see in this slide provides an example of the fine resolution we can achieve with this imagery, and how these algorithms can actually detect the piles of rubble. More recently, just this year, in fact, we have been working with Severn Trent Water to quantify greenhouse gas emissions from wastewater treatment assets. Drones were extremely useful when it came to collecting data path integrated methane concentrations and overall fluxes at an unprecedented spatial resolution. As I'm sure you know, the UK is committed to reach net zero by 2050, following the recommendations by the Committee on Climate Change. And that's why it's so important to quantify greenhouse gas emissions. The UK's water industry has made a pledge to do even better, though, and reach net zero by 2030. The fast pace at which this deadline is approaching is driving the industry to take up new technologies, and especially those that can provide accurate and rapid quantification of gas concentrations, enhancements, and fluxes. Currently, emissions are estimated based on guidelines set out by the Carbon Accounting Workbook protocols and using default emissions factors, but these are not asset-specific. To ensure targeted management of emissions, there is a need to enhance current monitoring capability and technology, and to obtain asset-specific emissions and fluxes as well. So drone technology could be the way forward. Within the context of methane emissions, drone technology deployment has been curtailed in the past decade by sensor weight and size. In other words, the sensors are just too big and large and heavy to fly. And until recently, there were not many commercial sensors that have achieved the required miniaturization to be embedded on board an unmanned aerial vehicle, but the solution is emerging. I'm talking about open path tunable diode laser absorption spectroscopy, but since that's a bit of a mouthful, let's call it TVLAS. The TVLAS technology emerged back in the 90s. But more recently, engineers have succeeded in miniaturizing this technology to the extent that it can be mounted on board small UAVs. If I remember correctly, the sensors were first made commercially available in 2013 and integrated to a DJI Matrix 300 RTK drone back in 2019. The sensor is currently known as the U10, and you can see a picture on the top right corner of this slide. Before the duo Matrix 300 and U10 became commercially available, the usually surveying mechanism for methane emissions were ground-based sensors or sensors mounted on cars, untethered to aerial platforms. The combined drone UTEN technology is much better because it enables on-demand rapid deployment and crucially can be used to quickly provide asset-specific measurements. It also avoids the need for in-situ measurements because it doesn't require the sensor to be located at the point of interest itself in order to take the measurement. We have successfully tried it with cake pads, anaerobic digesters, and secondary storage tanks. And if any of you are not familiar with those terms, they are all assets involved in wastewater treatment. If you are interested in knowing more about the results, you can find further details in the publication I have referenced at the bottom of the slide, or just get in touch with me to discuss further. Some other options we have explored for general asset inspection in wastewater treatment plants includes the use of completely autonomous drone surveying capability. The autonomous docking port, which was designed by Aerotech 8, is programmed to send drones to survey the assets of interest at specific intervals. It enables the automated deployment and implementation of extended flights over a wide area, which facilitates the frequent collection of high-resolution images at predetermined waypoints without the need for inspectors to be on site. In this way, it provides an integrated solution for the automated and autonomous inspection of assets within wastewater treatment plants. Now, I've talked extensively about drones, but that's not the only technology making a difference in my field. There are other emerging technologies that I use on a regular basis, which have also proved to be useful for environmental monitoring tasks. For example, back in 2015, if I remember correctly, we worked in collaboration with the Environment Agency to design an autonomous on-water robotic platform and use it to characterize river bathymetry and water velocity. The platform is equipped with an acoustic Doppler current profiler, another mouthful, but commonly known as ADCP. And this is used to measure current velocities over a depth range. The vast amount of data obtained enables us to extract cross-sectional profiles of depth and velocity as and where required within the surveyed river reach. We pair this technology with simultaneous localization and mapping, or SLAM, a technology whereby a robot can create a map of its surroundings and orientate itself properly within the map in real time. SLAM involves the use of a stereo camera, which is basically two cameras positioned next to each other. These two cameras visualize the environment just as a pair of eyes would. The algorithms reconstruct the imagery and are able to calculate distances to and from objects using trigonometry. And this in turn enables the autonomous orientation and navigation of the platform. We are currently investigating how water quality sensors could be embedded into this platform. But we have already come a long way from the arduous business of measuring cross-sections using a pole and a metric tape. The combined use of both on-water robotic platforms and unmanned aerial vehicles is making all the difference. The final example I'll mention in this context is a collaboration with Università Politecnica della Marche, UBICA, and Istituto di Scienza e Tecnologia della Informazione in Italy, for which we have used underwater vehicles to map the impact used to coral reefs by anthropogenic activity. Perhaps this example is slightly off topic from the actual water sector and wastewater treatment plants per se, and could be the subject for another webinar, but I can clearly see how the same technology could be used for asset inspection and management. Now, I would also like to say a little about the economic implications of some of this new technology. We can understand this within the context of the so-called Fourth Industrial Revolution, which describes the way extraordinary technological advances are fundamentally changing the way we use technology for good. The speed at which digital, physical, and biological technologies are becoming fused is just unprecedented, as is their potential for transforming the world, and most tangibly in terms of their financial impact. For example, in one of their reports, the Boston Consulting Group emphasized that within just 10 years, full-scale digitization could help global industries save an estimated $1.8 trillion annually. And in a study carried out in Australia by Deloitte back in 2020, the cost savings of using drones were estimated to be $9.3 billion over the next 20 years, approx, with 2.5 billion on agriculture, forestry, and fisheries, 2.4 billion in mining, and 1.34 billion in construction. Closer to home, actually, the UK government commissioned a study in 2022 on the effects of drone activity in coming years. It was entitled Advancing Airborne Autonomy, Commercial Drones Saving Money and Saving Lives in the UK, and is available on gov.uk. The authors estimated that by 2030, drones could contribute up to £45 billion to the UK economy. And in fact, even the use of drones for environmental surveying tasks will contribute towards the UK's economic growth, because as I've described, it has already increased surveying efficiency by enabling the collection of vast amounts of data in a reduced time frame. Surveys that require an entire week to reach completion can now be conducted within a single day. And overall, drones enable faster, less costly environmental surveying without sacrificing accuracy for most applications. The increasing affordability of drones in the market has enabled rapid uptake of the technology, with some platforms costing as little as £500 and enabling the collection of extremely high-resolution data. Moreover, low-weight platforms are easy to transport and enable fast deployment. Even larger, more expensive platforms above 30,000 have additional benefits that justify the price, as they enable the integration of heavy sensors for multiple parameter monitoring. And with these platforms, there is a further added benefit of wide area coverage. Of course, the initial capital investment is more substantial than for traditional ground surveying approaches, reaching up to 6-digit figures when multiple sensors are purchased. But these costs are rapidly recovered through increased surveying frequency and wide area coverage, which should also take into account the effectiveness of such platforms when it comes to surveying areas that would otherwise be inaccessible or locations that present a high risk, because increasing the safety of environmental surveying tasks is another major benefit. So, within this webinar, we have covered how multiple technologies can be used for surveying purposes within the water sector, with a special focus on drones. We have highlighted how such technologies significantly enhance our environmental monitoring capability, and how the data they provide can inform management decisions, as well as talking in more general terms about the cost effectiveness of such technologies. The list of technologies and applications provided here is not exhaustive. I have simply drawn on my own day-to-day practice and experience, and I'm sure many of you will have referred to a different range of emerging technologies in your own practice. So it would be wonderful to hear about them in our Q&A session. There is always a chance that our discussion will spark ideas for joint collaborations and even more technological integration. After all, many of the innovations I have been describing were either initiated or catalyzed by professional seminars and webinars like this one. So there are many exciting possibilities ahead of us. On that note, I would like to conclude my presentation, and thank you very much for listening. Thank you.
Well, no, thank you, Monica. That was a great presentation. I think it was particularly how emerging developments for technology, for data, for environmental management interact with one another, and how that's shaping the work that you're doing. And in that context, of course, it's really interesting always case studies of how that factors in, an example in Cockermouth or the monitoring for emissions from wastewater. It's all such a fascinating topic, and I know there's lots of dimensions we'd all like to explore further. So let's hop right in. Attendees, if you have any questions, please do continue to pop those in the Q&A box, and I'll put those. But I do want to pick up on that question of technology and data just before we go to the audience questions. Your closing remarks there. Naturally, it does sound like one of the crucial elements was at times quite reliant on using a pole or using a rope. Or indeed any of these other things which have now been replaced by novel technologies. I wonder if you have any thoughts on where technology may take us in the future. Are there any areas where we're metaphorically still using a rope, as it were, where we might gain a lot from future technological developments? Or maybe if that's too specific, just where you think data and technology might take us in the future?
I think there is a scope to include further enhancements, technological enhancements, when it comes to greenhouse gas emissions monitoring. Perhaps that will be one of the areas where we are going to see the faster and the largest enhancement and improvements over the next few years, driven by regulation, the need by the sector to actually monitor the emissions, and also by the fast pace at which the technology is advancing in that realm. Many companies are going to be in need of characterizing a scope 1, 2, and 3 emissions, and that will automatically decrease the demand for portable sensors that can actually give you some readings of the different set of gases we are interested in. At the moment, that portfolio of sensors is quite limited, quite reduced. But I can see that in the upcoming years, we will have a wider range of cheaper sensors, fast deployment of sensors, and sensors that can actually be integrated into UAV platforms for fast deployment.
Amazing, thank you. And we've got a question, actually, a great question that's come up in the Q&A box, which takes us, I suppose, a specific example of technological and data developments, which is more about opportunities for monitoring river or coastal water quality remotely. So what opportunities might there be for the remote monitoring in river or coastal water quality specifically?
So for freshwater ecosystems, there will be specific platforms that can be deployed underwater for the collection of water quality parameters and the automated characterization of such parameters. We have different stations distributed across UK that serve the purpose, but perhaps the maintenance is slightly cumbersome, cost-effective constraints apply there. I can see perhaps platforms that rather than being just fixed to a single point are able to navigate the water course and then able to collect information from up in the catchment down to the river mouth, obviously with the usual stops, but a continuous of information rather than just snapshots of what's happening in particular points. That could be quite useful. In terms of coastal monitoring, I can see obviously the use of satellite imagery. That would be one of the things that will provide information about coastal degradation, erosion. Medium-range satellites, we may be able to increase the resolution of the imagery that we are collecting. But if that's not sufficient to see how the coastline is being degraded in terms of erosion, we can see the use of drones, and in fact we have already seen the use of drones to monitor that particular aspect. So high resolution imagery at 1 or 2 centimeters of resolution, giving you high detail on what's happening. There's the added water quality aspect of it, which can be overcome with autonomous or semi-autonomous platforms for water quality monitoring, which I think is also a high requirement at the moment, given the number of challenges we are facing with sewage water reaching the coastline.
No, thank you. That's really interesting. And I suppose it almost takes us to one stage beyond the question, really. And I don't know if you'll have any perspective on this, but one of the things in the project we've come across is going beyond autonomous monitoring for data, for information, to this question of autonomous regulatory systems. do you think there's any kind of future for a system that is using these really robust real-time monitoring insights to automatically affect regulatory regimes? So, something like fine rates, abstraction licensing requirements, or even something like hosepipe bans, I suppose. Do you think there's any kind of future for taking it beyond monitoring to autonomous regulation?
I think it's absolutely feasible. Perhaps not right now, because it requires quite a lot of data collection and analysis in pretty much near real time. But with the use of artificial intelligence, for example, and the assessment of all the data collected at strategic points, one could see how such information could automatically inform about thresholds that need to be met and how these thresholds are changing over time to reach a better situation. It's also sensible to think that there will be someone behind the scenes, obviously, overseeing everything. Not everything will be left to the technology in itself, but it's easy to see how these things could map out in terms of using the technology for good.
Absolutely, really, really interesting, and I think that perspective really cuts through your whole presentation, is that there is an element of doing good as a result of this. We're not just doing data collection for the sake of data collection. It is all tied into these things that we care so much about. The other thing I wanted to pick up on is the other thing that you mentioned at the end of your presentation, which is about collaboration. And I mean, as we know, interdisciplinary working in the environmental sciences is increasingly important, but it can be quite difficult for those who aren't used to working in that way. I wonder if you have any advice or any insights into interdisciplinarity for those people who might be looking to connect up a bit more and be a bit more interdisciplinary in the ways that they're working.
So the majority of projects I have been leading have been multidisciplinary. I think it's definitely the way that research and the delivery of environmental projects is going to move forward, given the fact that everything is interlinked. There is perhaps a piece of advice there, or a lesson to learn, which is the fact that each discipline has its own terminology and jargon, and sometimes we spend quite a lot of time trying to understand that. It works as a barrier when we all mean exactly the same, but we are unable to communicate just because we are calling something specifically in a different term. Perhaps there's a need for standards there on how we use the technology, just to speed up the way that we communicate and we work together. But definitely, I mean, as challenges are being addressed and we are moving forward, there's a real need to absorb more of that terminology and get to work together to address the challenges that are facing us and the challenges that will face us in the future.
Yeah, that's a good point, I think, well made. And it's only going to work if we can work together. I suppose the other question within the multidisciplinarity space is what we can learn from each other, even when we're not working with one another. So the question, I suppose, would be, do you think there's any best practice in the work that you're doing that you'd like to see air quality professionals or land professionals or any of the other environmental sciences picking up? Things that you think that you're doing maybe with technology that could be interesting to see develop in other specialisms?
Yes, much of the technology could be transferred to other areas. For example, yes, what we have done, for example, with the wastewater treatment plants, where we were measuring methane, it's something that could be applied to other industries and other environmental assets. So there's a potential to transfer knowledge there. I mean, many of the things that we have tried are state of the art. So it's perhaps the first time that is being done, and such use has not been explored in other areas. So if anybody is open to explore the use of particular sensors or technologies in their particular industry, we will be really interested in doing that. In terms of more general lessons that we can transfer to other sectors, perhaps using emerging technologies, what is driving us to do is to think ahead about the planning of how the technology needs to be deployed, and then the perception of that technology. So in many cases, when we have found that when we are trying to use drones, society does not see the positive benefit of drones, because usually have a bad press, and they are also linked to unexpected situations around the airports, let's say. So there's a need there for advanced planning and assessment of the perception that people have of that particular emerging technology. And perhaps this is a lesson that can be transferred to other sectors. So when we are talking about multidisciplinary projects, when we are talking about working together, maybe there is a need also to get the perception of the public and educate the public that there is a need to work together multidisciplinary on that specific topic.
Yes, definitely. I mean, and in terms of that public engagement, educating the public about what technology actually means and why it might be good for them, or something that they maybe don't need to worry about as much as they might be worrying, or indeed just helping them to address those worries. Do you think, what do you think about the role of the environmental sciences more broadly, but particularly the kind of science that you're working with in public engagement over the next 20 years or so?
I think there is going to be a push for knowledge transfer at different levels. When we say public engagement, we are thinking about not only end users, we are also thinking about government and policy as well. And the end of that knowledge transfer will not be successful if we don't consider the full chain of people, stakeholders that are actually going to be using the technology, understanding the technology, regulating the technology. So for us to be able to achieve that and increase the pace at which solutions are being put together to address environmental challenges, we need to make sure that we dedicate more time to transfer the knowledge that we have gained with a specific projects. Not necessarily within research, that's not what I mean. What I mean is that every single project that we are carrying out is bringing a wealth of knowledge. And sometimes that doesn't reach a wider audience. So I think that perhaps in the future, we are going to be dedicating more time to make sure that those messages are coming across.
Yeah, no, I couldn't agree more, really. That's an excellent point, I think. And I know that colleagues operating in the land space have had the same kind of issue with collecting a lot of data, learning a lot of things on projects, and then never using them anywhere else, never telling them to people. So I think you couldn't be more right with that. I wonder, though, what does it mean for the skills that we have in the environmental workforce? Because there's a lot of new things in here that we haven't done in the past. Do you think we have the skills that we need, or do you think we might need more skills in the future?
That's a very good question, actually. I think, let me phrase this properly. So I think we have the skills that we need, but I think they are in pockets. So it doesn't mean that the skills exist and people have these skills, but they may not be based with the person that actually needs these skills. So there is a need to, again, going back to the multidisciplinary job, there is a need to bring the people with the right skills to address the right problem. And it's very difficult for a single person that is faced with an environmental challenge to have the full range of skills that are required to solve that environmental challenge, because as multidisciplinarity increases, the number of skills are more varied and more convoluted. It takes longer to learn them. So the only way of addressing that is by bringing more people working together. The skills are there in one way or another, but it's just a matter of actually linking them together for the specific challenge that they are going to resolve.
That's a brilliant point. That I hadn't really thought about it in terms of the multidisciplinarity aspect, but I think that's a really smart connection to have made. I suppose then I've got one final question for you before we wrap up, which is, bringing all of this together and thinking about the future of the environmental sciences as selfishly we would like to, because we're working on this project. I wonder what you see the path being like. Do you see us moving in a good direction on this? Do you think it's maybe less optimistic than that? What do you think your priorities for the future might be? I would suppose is a final question.
Okay, so I think the pace is slower than I would expect it to be, or I would wish it to be. I think we need to speed up, especially given the fact that we have an underlying trend, which is climate change. And if we don't move fast, it may be too late to be anything to resolve the challenges that are being presented. Towards the future, I think that we are going to have an increased focus on the use of technology, especially within the context of greenhouse gas emissions. So I think this is where we are going to be panning out research and focusing research to make sure that we meet the net zero targets in the years to come.
Well, fair enough. Well, a very sort of serious set of challenges to end us on there. But I think you've also given us throughout the presentation a lot of reasons to perhaps be a little bit optimistic that maybe we can do it, because there's technology and there's the right people in the right places, maybe. So maybe some conditional optimism that if we approach it in the right way, we might be able to face down the challenges. Well, I mean, that's all we have time for. So thank you so much for answering those questions. And thank you once again, Monica, for presenting what was an excellent webinar, full of really fascinating insights into the way that all of this work has been changing, really bringing these abstract ideas of technological change into such clear and practical applications for environmental science. For now, that's it from us for today, attendees. Thank you for logging in, and I hope you found that beneficial and informative. Don't forget to record your attendance at this webinar in the IES CPD tool. You can do that by logging into the members area. The webinar has been recorded, and it will be made available on the IES website and our YouTube channel. If you're watching the recording on YouTube in the future, please do subscribe to our channel, like the video, and hit the bell to gain notifications for new content. Coming up soon, we've got many more events which might be of interest to you. Most importantly, this webinar series will be continuing throughout the week as we continue to look at the changing nature of environmental work. So on the 27th, that's Wednesday, we're going to be joined by Jonathan Atkinson to talk about his work in the land sector. And then on Thursday, that's the 28th of September, we'll be bringing together all of these discussions about individual specialisms with a panel discussion on interdisciplinarity, digging into those big conversations which are at the heart of everything that we do as environmental scientists, and indeed which have kind of been a theme of the last couple of questions here as well. And then finally, to wrap up this week, we're going to have on Friday the 29th, our next big horizon scanning discussion event, where all of you can join the conversation directly and share your voices on both the future of the workforce and indeed the future of environmental jobs themselves. And you can sign up for all of those events right now on the IES website, where you'll also find details of our upcoming training workshops and some of our other events. If you're interested in our Future of ES23 horizon scanning work, you can find all the details on our website, or you can just send us an email and get directly involved in that project as well as we move into the final stages. For now, though, thank you again to Monica for a great webinar, and thank you to everybody else for attending and taking part. For now, have a lovely rest of your day, and see you all again soon. Goodbye.